section, we spent most of our time just working with Ohm's law. And we're still going to do a little bit of work with circuits, but not to the extent that we did in the last one. So when we're talking about the energy of an electric current, so energy can be defined as work being done. Okay. So 1 joule of work is done when 1 coulomb of charge is moved through a potential difference of 1 volt. So we're going to look at a few ways in which we can look at calculating how much work is done or how much energy is used. So what we want to do is number one, we want to be looking at power outputs, okay, and power efficiency. So if you take a hot plate, for example, or a kettle, the amount of power that's going into the kettle, how much of it is being used to actually heat the water? So it's about efficiency. So that's what we're going to look at a little bit as we go through this. So the first equation that we work with is Y equals Q times V. So Q is your charge, V is your potential difference of a volt. So work is equal to Q times V. Now using substitution methods, using the substitution method, I also know that my I, in this case, was equal to Q over T, which was my, I amperes is the amount of coulombs that pass a given point in a given amount of time, right? So that's what current is. So I can do a little converting, I can change, and the very first equation that we want to work with is work is equal to V times I times T, because I change this to Q equals IT. All right. Now what we do then, so this allows me to find the amount of energy used if I know my potential difference, if I know my current, and I know the amount of time that it's acting. All right. So there's one thing I can do it for. Now, if I just manipulate this here, all right, and I put instead of using V, I use IR, I can get I squared RT as one of my equations as well. So all I've done is taken the IR right here and substituted it in for V. Okay, so these are two equations that I can use. Now, this one deals with potential difference in current as well as time. This one is, what if I don't know the potential difference, but I do know the current and I know the amount of resistance over the whole circuit? I can use I squared RT to help us solve it, okay? The third one refers to Joule's law. So the heat developed in a conductor is directly proportional to the resistance of the conductor, the square of the current, and the time the current is maintained. So that's essentially what this is. This is what we refer to as Joule's law. So the heat developed in a conductor, or energy in this case, is directly proportional to the resistance, the square of the current, and the amount of time that the current is maintained. So that's what we refer to as Joule's law. The electric energy expended in the resistance is directly proportional to the heat energy that appears. So the third one is this. Work is equal to J times Q. Now this is a capital Q. This is not charge anymore. Okay? So J is a constant, joules constant, 4.19 joules per calorie of heat. So that doesn't change. Q
Rory.
Yeah.
Rory has to restart her thing. It's not working.
Okay. Thank you. I'll slow down then. Okay, and Q is the quantity of heat in calories. All right. Now, what we want to do is we want to be able to find out how much energy or heat is expended when we use this. Okay, that's what Q is. All right. So when we talk about, when you're working out, how many calories you burn. All right, that's what you're expending. You're expending heat out of your body. You're getting rid of the calories that you burn. Right. So when we do it within the electric circuit, we work with work and joules constant, or we can use this guy right here, part of Joule's law, and we can get I squared RT over J. All right. And what that Q measurement is in calories. Now, most of the time when we're working with power and electric circuits, we burn a lot of this, all right, and large amounts. So we work with kilocalories. But when I'm solving things, I want to make sure that I'm using just the very basics. So I want to work with just joules per calorie and calories, and not with kilo until the very end. Okay. Now we're going to get into a bit of chemistry, somewhat, in working with this. So another way of finding Q. This is not a physics one. This is one that you would work with in chemistry. So Q is heat being burnt, right? Well, you guys would work with it like this. MC delta T. So M is the mass of the substance, right? So you try and find out how much heat is used. So mass of the substance. C is your specific heat constant. Okay? And T is the change in temperature. So the only thing you don't know is C is your specific heat constant. And we get that off of a chart. Oh, here's the other thing. Did all of you take a physics book home? Textbook?
I did, yeah.
Okay.
I did. No. Yeah, I did too.
Okay, perfect. Okay, so because that's where the charts are. The charts are in the back of that book. Okay, for specific heat constants. All right, and the specific heat constant for one is just 1. Sorry?
I'm tilting the camera just a little bit down. So
Oh, yeah.
See the rest of the board.
Is that better?
Yeah.
Okay. Okay, so MC delta T. So this is one that you would have used in chemistry when you're studying the amount of heat transfer or the amount of heat being used in a reaction. Okay. So the first problem that we're going to look at, and this is, so I don't know if this is in your textbook or not. Let me have a look. Just one sec. Yeah, it is. So, Mary, if you want to open to page 451 of the textbook, you can follow along the example I'm about to do on the board, okay? All right, so again, our goal in this section, one of our goals is to work with heat efficiency and power being produced. So it says the heating element in a percolator has a resistance of 22 ohms.
Sorry, where are we again?
451.
Oh,
So this is the example on the sheets here. So if you have it in the, you can also look at page 451 in the book. Is designed for use across a 117 volt circuit. It says, how long will it take to heat? So I need my time. It take to heat 1 kilogram of water. So I got a mass of 1 kilogram. I'm going to change it to grams. I don't want to work with kilo anything at the moment. I'm just going to keep it very basic. This will kind of ease your pain as we go through this. We're talking about water. So the specific heat constant for water is, it takes 1 calorie, of heat sorry, 1 calorie of heat to raise the temperature of 1 kilogram of water 1 degree Celsius. So the specific heat constant is 1 calorie per 1 kilogram degree Celsius. I just want to make sure I got that right. Yeah. Okay. Oh, sorry. I did make an error here. I want this to be in grams. So if I got calories, I've got grams. If I have kilocalories, I have kilograms. But I don't like to use kilograms, like I said. I make more mistakes that way. Okay. So anyways, raise the temperature from 20 to 100. degrees Celsius. Assuming no loss of heat to the surroundings. All right. So I've got a lot of information here. Okay. So somehow I need to find out the amount of time it takes to raise 1,000 grams of water 80 degrees Celsius. And my output for my power is 22 ohms and 117 volts. Okay. So I'm going to use heat to figure this question out. So up here I have Q equals I squared RT over J. And if I arrange that to find out what my time is, I've got QJ over I squared R. Okay? So that's my time, right? So what do I need? Well, I've got J, because I know J, I didn't put that in here, I should have, is 4.19 joules per calorie, right? So I have J. I don't have I though, do I? But I do have R. So I've also got V here. So what I need to do is, what am I missing? Out of these 4 pieces of information, what are the 2 things that I'm missing? I'm missing Q and I'm missing I. So where do I get them from? Well, I can get I from here, right? And I can get Q from down here. So using my V and my R, I is equal to 117 volts over 22 ohms.
5.318.
5.318 amps, perfect. Got it? And then down here I have Q equals MCT, so it's 1,000 times 80. So my Q then is actually 80,000 calories. All right. So to find the amount of time it's going to take to heat the water All right, so what I've got here, I just want to explain this a little bit better. Basically, I'm heating the water using a hot plate, let's say. It can be anything but a hot plate, let's say. And this is the information that I'm given on the hot plate. I'm given the resistance and the voltage of the hot plate. All right? I want to find out how long it's going to take for this to boil water, to boil 1,000 grams of water. That's what I'm attempting to find out. So I go 80,000 times 4.19 over 5.318 squared times 22. Okay, so I'm going to punch that into my calculator. $538.75 seconds. Kaylin? Have to have brackets on the denominator. So 80,000 times 4.19. You get it?
I got 540.77.
Did you use 5.318?
Oh, shoot, I accidentally pressed 0 instead of 1. There you go, that's a problem.
Okay. Mary, thumbs up if you got it. Okay, Daylin, still working on it?
I think it's because I was still in radians.
Has nothing to do with radians.
Oh, I did.
There's your keystrokes. Can you see that? Let me make it bigger. There's your keystrokes.
I got it.
Okay. Okay.
I didn't square it.
Okay. Good enough. All right. So again, what we're trying to accomplish here is we're trying to find out, by given a certain amount of power, how efficiently does something heat? Okay. So that can depend on the amount of output of our current with our voltage. That can depend on the type of metal that we're using, because that affects the resistance. Okay, those are the types of things that we want to look at as we move forward into this. All right. So the last thing we're going to look at today is, there's a couple questions there in 452. You guys can try those after. But is power itself. So what is power? Power is the rate of doing work. So we're measuring the amount of work being done over a given amount of time. So first equation that we are going to work with, they have it down as equation 6. I don't know. Power is equal to work over time. Okay. And then again, using V equals IR and work equals QV, we can change these. So I've got power is equal to V times I. Using Ohm's law, I can, so V equals IR. Substitute that in for V. That gives me power is equal to I squared R. And V squared over R as well. If I change I to V over R, substitute it in here, I get V squared over R. So these are 3, 4, really, but these guys right here, all are the same equation. Okay? All right. Now, where this applies to circuits. So when we are looking at circuits, very basics with circuits. So we've got, this is R, this is R, this is my load resistance, okay? Excuse me. So I've got R, RL, RT, E, I, R. And now we're going to add P to our chart. So not much has to change. All we're doing is we're going to add P to our chart. Okay, now we're not going to do elaborate circuits like we did in the previous one, but the one thing that you need to know, so this is on page 5 of my notes here. There's one piece of important information in here that we have to know. Okay, so the maximum transfer of power. So the transfer of maximum power to a load is important. An example, a starter motor of an automobile engine. So we want to convert and we want to transfer as much power as we can to it. So Mary, if you're following along, this is on page 453 and page 453 and 454, Mary.
Oh, okay.
Okay, so the maximum power is transferred to a load. So the maximum power is transferred to here. When I want maximum power, the load resistance has to equal what the internal resistance is. So in order to get maximum power to your load, now remember, this is inside the battery. Little r is inside the battery. So to get maximum power on the outside of the battery, out here, my load resistance has to equal whatever the internal resistance is inside the battery. So on number 5 on the sheet here, that's what this is showing. This just explains it using numbers. What you need to know is that if it asks you to find the load resistance, you change your load resistance from whatever they've given you to whatever the internal resistance is. And if they're equal, that's how you get the maximum power to the load. Okay? And then the last thing it talks about is purchasing electric power, but we'll deal with that tomorrow. But that essentially covers this whole thing. Everything that we've done in here. It's a very short unit, but there's a number of things that are fairly important within that unit itself. Okay? Yeah.
So say we don't go to school for a while.
Okay.
And this is only about to gave us, right?
Yeah, well, what I'll do is when we're done with this one, I will scan and I'll put, you missed the conversation I had with the girls earlier, unless you were listening to it on YouTube Live or on YouTube Live here. I'm just going to shut YouTube off for now. one of the things I said is I'm